Hello everyone, welcome to a class on basic electronic circuits. The topic for today is diode clipper. Before we start off with the analysis of clipper circuits, let's just revise the biasing conditions for diode. For a diode, if the anode of the diode is connected to positive plate of the battery and cathode of the diode is connected to negative plate of the battery, then we say the diode is forward biased. Let's look into the equivalent circuit for the diode when the diode is forward biased or reverse biased. When the diode is forward biased, in ideal condition, we'll consider it to be a short circuit, but we are aware that there is going to be a drop across the diode. For silicon diode, it will be approximately zero point 0.7 volts, whereas when the diode is reverse biased, it will act as an open circuit, or I may say in actual condition, it is offering a very high resistance. The circuit shown here is a basic clipper circuit with one diode, resistor and a sinusoidal input source. The input applied here is 10 volts peak to peak. That means the peak value is going to be 5 volts. When the diode is forward biased, we'll consider a drop of 0.7 volts, and when the diode is reverse biased, we'll consider it to be an open circuit. The diode will only conduct for all values of V greater than 0.7 volts. For any value of V less than 0.7 volts, the diode will remain reverse biased and will act as an open circuit. Therefore, the output for this entire phase is going to be equal to 0. This is an equivalent circuit when the diode is forward biased. Now, V0 is always going to be equal to the instantaneous value of input voltage minus the diode drop, which is 0.7 for silicon diode. For example, when V is equal to 5 volts, V0 will be equal to 5 minus 0.7, which is equal to 4.3 volts. Now let's look into the input and output waveform for the circuit. As we discussed, the output is going to vary from plus 4.3 volts to 0 volts, in contrast to the input that is varying from minus 5 volts to plus 5 volts. The circuit flips off the negative part of the input signal, and hence we can call it to be a negative clipper. Moreover, the diode is in series with the input source, so we can call it to be series negative clipper to be more precise. The same circuit, if we reverse the direction of the diode, the resultant would be a series positive clipper with a maximum peak at minus 4.3 volts and a minimum value of 0 volts. The circuit shown here is a bias clipper. We started the analysis with calculating the input voltage, after which the diode becomes forward biased. Now as you can see, there is a 2 volts battery connected between the input source and the diode, and the diode would require 0.7 volts to start. Therefore, input required to turn on the diode would be 2.7 volts. That means the diode will only conduct after Vin is greater than 2.7 volts. Next thing is to calculate or find out the expression for VO. To find out the expression for VO, we'll apply a KVL in the loop. So expression for VO would be Vin minus 2 volts battery minus the diode drop, which is 0.7 volts. So for example, at Vin equal to 2.7 volts, my output V0 would be equal to 2.7 input voltage minus 2 volts battery minus 0.7 volts diode drop, which is equal to 0. And at V equal to 5 volts, my V0 would be equal to 5 minus 2 volts battery minus 0.7 volts diode drop, which is equal to 2.3 volts. So now you can see that in the waveform, the output is varying from plus 2.3 volts to 0 volts. Let's look into one more example of bias series clipper. As you can see here, the diode is connected between the input source and a battery of minus 2 volts. Now, as in the earlier case, we'll first find out the input voltage to make the diode forward bias. The input voltage required to turn on or to make the diode forward bias would be equal to the diode drop minus 2 volts. That means that would be required to make the diode forward bias would be equal to minus 1.3 volts. So for all values of V greater than minus 1.3 volts, the diode would be forward bias. Next, let's look into the expression for V. Again, for expression for Vos, we simply have to apply KVL in the loop. So now V0 would be equal to Vin minus diode drop, which is 0.7 plus 2 volts. For example, if my Vin is equal to 5 volts, then my output would be equal to 5 minus 0.7 plus 2, that is, it will be equal to 6.3 volts. For all values of Vin less than minus 1.3 volts, my output would be equal to 0 volts. So as discussed, the output will vary from 6.3 volts to 0 volts. Let's look into one more example of bias series clipper. Here there is a minus 2 volts battery connected between the diode and the input source. Again, let's find out the input voltage, after which the diode will start conducting. As you can see, the input voltage required for the diode to conduct would be equal to minus 2 volts of the battery plus minus 0.7 volts. So the diode will only be forward biased for all values of V less than minus 2.7 volts. Diode will be reverse biased for all values of V greater than minus 2.7 volts. Now let's look into the expression for VO. VO would be equal to V in plus 2, that is the battery voltage, plus the diode drop, which is 0.7 volts. For example, if Vin is equal to minus 4 volts, my VO would be equal to minus 5 plus 2 plus 0.7, which is equal to minus 2.3 volts. So as discussed, the output is going to vary from 0 volts to minus 2.3 volts. In this circuit, the diode is in shunt with the input source, and hence we call it to be shunt clipper. Note that V0 is exactly across the diode. So when diode is forward biased, a drop of 0.7 will be observed across the diode. This will also be seen at the output node. When the diode is reverse biased, it will act as an open circuit, and hence V0 will be in shunt with Vin, and V0 would be equal to Vin. As we can observe from the waveform, when the diode becomes forward biased for Vin greater than 0.7 volts, the output is equal to 0.7 volts. For all values of Vin less than 0.7 volts, when the diode is reverse biased, the output simply follows the input. Let's have a look at only the output waveform. Now you can see that majority of the positive half cycle is clipped by this circuit. Hence, we can call this circuit to be shunt positive clipper. Similarly, if we just reverse the direction of the diode, what we would be getting is shunt negative clipper. Now let's see a bias shunt clipper. Like in the case of bias series clipper, we will try and find out the input voltage for which the diode will remain in forward bias. As you can see, the anode of the diode is connected to plus 2 volts battery. We would require a 0.7 volts drop across the diode for the diode to turn on. So V in that should be applied should at least be equal to the diode drop minus 2 volts. So the diode will remain in forward bias for all values of V in less than 1.3 volts. During this phase, the output voltage would be equal to minus 0.7 voltage drop across the diode plus 2 volts of the battery. So V0 would be equal to 1.3 volts. V0 will be equal to 1.3 volts for the entire negative half cycle and for all values of V less than 1.3 volts. The diode will become reverse biased for all values of V greater than 1.3 volts and it will be represented as an open circuit. Now V0 would always be equal to Vd plus 2. But the value of Vd will change as Vin varies. So first let's write an expression for Vd. Vd would be equal to V in minus 2. This can be easily found out by applying KVL in the loop. Now let's take an example. When Vin is equal to 5 volts, Vd will be equal to 5 minus the battery voltage of 2 volts, which is equal to 3 volts. Therefore, VO would be equal to voltage drop across the diode, which is 3 volts plus 2 volts of the battery, so 5 volts. So as discussed, the output varies from 1.3 volts to 5 volts. Now in this circuit, the cathode of the diode is connected to plus 2 volts battery. So the diode will remain forward biased for all values of V greater than 2.7 volts. The output during this phase would be equal to plus 0.7 volts draw across the diode plus 2 volts battery, which is equal to 2.7 volts. The diode becomes reverse bias for all values of V less than 2.7 volts. Now expression for Vd would be equal to Vin minus 2 and expression for Vo would be equal to Vd plus 2. For example, when Vin is equal to 2.6 volts, Vd would be equal to 2.6 minus 2, that is equal to 0.6 volts, and V0 would be equal to 0.6 plus 2, that is equal to 2.6 volts. Discussed earlier, output will vary from plus 2.7 volts to minus 5 volts. Thank you.